I promise that this will be an easy topic since you are familiar with databases, you know a lot about them. And also, you might also know that probably substructure search and similarity search are the most frequently utilized cheminformatics or virtual screening technology in general. And I'm in a lucky situation since András Wolfold talked about the history of these cartridges. So now you know why we are having this application study and what are the tools we will use. JOC, the JChem Oracle cartridge, that's the major cartridge, which is quite on the market for a while. The JChem PostgreSQL cartridge and the Coral, the latest next generation cartridge, will be compared to each other on 3 different data sets from 3 different angles to be able to measure their performance. So therefore, we have collected a number of structural queries like drug molecules, rings appearing frequently in drugs, as well as some substructures with query features. And the first set was the MQ database, which is kind of a plain database without any relational database tables, only one table with structures and IDs to be able to assess the pure speed and the speed improvement in between our previous technology and the next generation technology. Now I'm showing the results in terms of the fold improvement after summing up the elapsed time for all the queries and comparing it to JChem Oracle cartridge. So therefore, you are seeing 2 bars. If in case of substructure search, one means that it was with equivalent speed. Wolfie had already mentioned substructure search with limit, so we are only asking for the first 100. In this case, you can see that 15, 16 times or fold speed up was measured. And for similarity is 20 times faster and almost 30 times faster with similarity limit. And there is this new sorted chem index. Therefore, these substructure search hits are ordered according to their relevance immediately. So as you can see, 10 to 30 times speed up fold improvement was achieved, which is a nice achievement. However, we see one case when it was just as previously. So we will investigate this in more details. Now I'm plotting the elapsed time per query in a function of the hit count. So how many hits are retrieved from the database? If you can remember, it was 42 million structures in the database. And as you can see, at about 400 milliseconds, the black dots are the JOC, the gold ones are the Coral, and the green ones are the Postgre cartridge results, individual results. And as you can see, if it is below, then there is a speed up. If it is just next to each other, that's quite the similar speed. So the conclusion from this side is in a range of 2 tens of thousands of hit retrieved from the database, we see a nice speed up. However, when you are retrieving millions or tens of millions of hits, which might not be a realistic case, since that's not an online and on-the-fly analysis in most of the cases, then the speed up is not that trivial or not that univocal. But still, what we can see that for a reasonable number of hits, the new engine performs quite well. And if we are comparing the ratio, that means there is a sustained 8 to 10 times speed up in this range, while in the really high number of hit count, it just goes to and reaches the 1, or in some cases goes below 1. So what we can conclude is that there is a significant speed improvement for substructure search, even with sorted chem index, so with relevance sorted, and therefore you can utilize the limit searches to be able to show your clients the most relevant hits first. And also, in similarity searching and substructure search, where you have reasonable number of hits in a large database. But that's not the reality, since you are not only interested in compound collections, you might have additional data, biological data, project data, and you have a complex relational database. Therefore, you would like to utilize cartridge technology and to be able to rely on query planning and all of the magic provided by the relational database management system. Therefore, the second assessment was done on Campbell, which holds 1.8 million structures and 15 million activities with the very same structures. However, we wanted to mimic the real-life use case. Therefore, we come up with a combined query where we define the target. Activity should be in nanomolar. There should be a substructure element as a to be retrieved, and a moiety that shouldn't be retrieved among the hits, and joined 4 tables. You can see the SQL here. So this is a combined query that's realistic. You're interested also in the biological results and the navigation in the chemical space as well. So this is the complex query results measured on the Campbell database. As you can see in the Coral, there is a 3-fold improvement in terms of the elapsed time, the sum elapsed time, where in case of the Postgre cartridge, it's 13 times faster. And you can see the results for substructure, similarity, and similarity limit. Again, the substructure is close to 1, but if we go deeper into this direction, we will identify that those hits that are with a lower number of hit counts are retrieved faster. So, okay, we can query with complex queries, combined queries, the database, and it will perform much better than the previous engine did. But these 1.8 million structures and 15 million biological data might be an order of magnitude smaller than a large company's database or a real large database. And therefore, we decided to go for a next exercise with a test case when we have 10 million molecules and 30 million just numeric values. In 2 tables. So that's an artificial test case when we have 5 times as many molecules as in Campbell, and we mimic to have 30 million biological results. And when we arrived to this point, we discovered something that we thought worth sharing with you. That's not goes to the direction of complexity, but to simplicity. So that's kind of a detour in this story, is that the relational database management systems insist on planning. So even if you have a straight road without crosses, you only have a substructure search, it will ask for a query plan. It will create a query plan, it will ask for cost estimation. In case of the PostgreSQL cartridge, the cartridge itself can evaluate the whole query, so it can decide not to do the cost estimation and save time with not calculating the cost, since for quick queries, calculating the cost might take longer than the actual query itself. But in case of Oracle, we did not have a chance to digest the whole SQL and to be able to figure out that there are no additional conditions. What's the effect size of this? If we can avoid planning, you can see the increase in the speed up, in the fold improvement from 8 to close to 50 times. So in this third test case, for 10 million compounds on a substructure search with limited queries, these are the ones that are retrieved really fast, then if you can somehow switch off Oracle query planning, then you can still increase further the improvement. That's also true for the old cartridge, and therefore the JPC did not have this cost estimation, but the previous Oracle cartridge speed also increased. Therefore, there is a slight decrease if you compare the ratios. But how can you achieve that? The JChem-based team had an idea that if you have a function in the in the statement, then Oracle will not ask for cost estimation. So that's the way how you can escape from cost estimation in case of Oracle. So if you have a system that can recognize that only chemical condition, only substructure search will be executed, then you can add a function that just returns itself and include this into your query, and then it won't do the cost estimation. So coming back to this test case, so now we have these numbers, and since we mimicked these numbers, we have control over selectivity, and we thought that we can play a bit to be able to test two flavors of how the search is done. One is the access mode and the other is the filter mode. In case of access mode, the index is used. In case of filter mode, it's running one by one the evaluations. So therefore, we had two cases. In one case, the data, so the additional condition was not selective, and we hoped that the chemistry will run in access mode. And in the other case, we put a condition that limits, so that's very selective. So there we have two conditions, one on this biological result, the other is on chemistry. And now we are playing which should be the more selective step in that, so that the database can decide how to execute these queries. So in case of chemistry access, as I mentioned, the data is non-selective. In case of chemistry filter, the data is selective. So these were the results on the combined query. And you can see a difference in between filter mode and access mode. And in case of filter mode, so that's the functional mode when it's executed one by one, the database is asking whether a given hit is a hit for this condition as well. The speed up is 2.5 or 6 times faster compared to the Oracle cartridge, while in case of access, it's just as before. This was a substructure search. However, we went into the query plans and evaluated the query plans, and it turned out that the system did not exactly behave as we hypothesized or as we wanted to have, since in case of the JOC, it did in access mode the filter cases. In most of the cases, in case of Coral, it was half and half, and JPC behaved just as you imagined in case of filter experiment. So with Oracle cartridge, we did not meet our requirement that in case of chemistry filter, it will do it in filter mode. Here you can see the results. This is the elapsed time, sorry, not the ratio, compared the JOC, so the Oracle cartridge, and the Coral in filter mode and JPC in filter mode. This is the 1-to-1 ratio. So that's the time needs for the old JOC to execute, and the dots are the time required for Coral and JPC. You can see that these are the individual points are around 10 times faster, and for case of Coral, it's in between 1 and 10 in most of the cases. But going back to this slide, still we have to evaluate the access mode. And again, in case of access mode, as you can see, when we have low number of hits, we see a nice speed up, and we have higher number of hits, we see less announced speed up. Which goes back, if we are plotting the hit count versus the elapsed time, to something similar what we have observed before. But here, these numbers are not that big. So we are not talking about million retrieved records. But keep in mind that this is the case when this is using the index. So that's less selective. We have another selective condition next to it. So the cartridge is doing the very same. It's running the index mode. It's non-selective. And the final hit count is a combination of this non-selective chemistry plus the selective additional data condition. But all in all, as you can see, in 10 million compounds with 30 million assay data points with non-selective queries and in access mode, still the performance is about hundreds milliseconds, and that's the speed improvements what we have measured. And that opens up new possibilities, as it was described by Andras Wolford. So the next generation cartridges offers you features built on this engine performance improvements. One is the asserted substructure hits. So you probably not want to drink the whole ocean to eat fish. So probably you are not looking for all the things, but the most relevant ones. You need the most relevant hits. And that gives you the possibility to think in a different way, think applications that offers agile search methodologies. And something that was not mentioned is that these engines are also offering a new so-called low memory setup to be able to tackle with large data sets as well. So thank you for your attention. That was the cartridge evaluation.